Okay, guys, let's continue with another chapter. This is called Delaunay triangulation, and in this chapter, we'll be discussing a specific way of triangulating the planar surfaces. And we will be trying to find a unique triangulation, and that will be the Delaunay triangulation. And in that triangulation, we shouldn't have actually any side inside this triangles. So we will be given a kind of points again on the plane, and we will try to triangulate with the help of this point. For instance, this is an example triangulation I'm going to make. It will not be properly probably an Delaunay triangulation, but right now it's simply an triangulation. You see, this is another unique triangulation, but the thing is that we shouldn't have any sides inside these triangles. This is the only requirement, and we will be looking for different ways, and we will have some rules to define this Delaunay triangulation. For instance, you see some examples here, a 2D and a 3D type of triangulation. Obviously, in the 3D version, we are dividing the region, the space, into some tetrahedrons. But for the 2D platforms, assume that these are our sides. And what is this one? Obviously, this is an Delaunay diagram, right? And again, this is Delaunay diagram, but this time it's 3D and the one on the left is 2D. What about these? This one is a kind of an triangulation of the same size, but we have a missing here. This is it. Once you have it, then that will be a perfect triangulation. And the thing is that this time we are using the given sides as the vertices of triangulation, or as the vertices of the triangles. And as you see, this is the Delaunay diagram. We use the same size as the sides of the Delaunay diagram, but this time in the triangulation, we use them as the corners of the triangles. And it's also the same for the 3D case, but this time, instead of triangles, obviously we have some tetrahedron. Any questions, guys? We can say that there's a kind of a relation between the Delaunay diagrams and the triangulation. In this chapter, we will discuss this relationship and try to find some ways to draw Delaunay triangulations, which is a kind of a perfect triangulation depending on your goal or cost function. Here's another example. For instance, this is a kind of an terrain map. You see some hills, some valleys. We have a hilly region here. We have flat regions. Again, some hills around, but they are all represented with the help of the triangles. So by simply using triangles, we can represent such a terrain. Again, it's a very difficult one. And you see the side view of that terrain. And we can have, we can map this 3D, let's say, triangulation on a plane, and you see they are all on the same plane, but we may assign some values to these corners, so that with the help of them, we can represent a kind of a terrain. So now we are going to discuss two examples and discuss which example is better representing the given terrain. You see there are two of them, A and B. We have a similar triangulation. The only difference is that in this one we have such an edge here. On the left and right hand side, we have this edge. So once you connect these 2 points to each other, by the way, these values are representing the heights of that vertices. So if you connect such a line in between, then that means if it's the center of that line segment, then the height of that point will be 955. But if you have another edge in between 10 and 36, then the midpoint of this line will be representing 23. Although they are highly similar, although we have the same number of vertices, same number of sides, we are actually representing totally different terrains. In this one, we have quite a hilly region here. There are hills after each other, but here on this right-hand side, we have a kind of a valley in between here. So this is the heights of these vertices are low compared to the heights of these regions. We have two hills, and in between them we have a valley, but here this is the same set of, actually they are all contributing to the same hill. So in summary, by simply flipping an edge, we can have completely different terrains. And this is also the same once you are doing some kind of meshing or other applications. If you modify the triangles, then the resulting representation will be totally different. So the thing is that if you have a triangulation which have small angle is bad. That will be our assumption. And we are looking for always triangles having larger angles. For instance, if you have kind of a triangulation, you see we have low angles all around here, large ones here. We don't want to have such a triangulation. Assume that we have the same shape, almost the same, and that will be much better. As you see, in this case, we flip this interior edge to this one, and you see that the angles are modified a lot. This time we have larger angles, and our aim will always be to find such triangulations having larger angles. We don't want to prefer smaller angles, and that's why we'll try to find a way to rank these triangulations in terms of their angles. Since let's assume that you have n number of triangles, then that means you will have some finite number of triangulations. Maybe let's say you have hundreds different triangulations for a given set of point P. So our aim will be to find the optimal triangulation, and in each case we will have the maximum minimum angle. So we are trying to maximize the minimum angle of these triangles. That will be our goal, and once you have it, then that means you have the Delaunay triangulation. The other ones, the other triangulations having minimum angles are not the Delaunay one. They are simple triangulation, but we are looking for the specific, for a unique triangulation which has the maximum of minimum angles. So these are the inputs, the points on the plane, and we will be dividing this plane into some subdivisions, and this subdivision is such that there will be no edge connecting two vertices, and you cannot add extra edges without destroying the planarity of the triangulation. Now let me illustrate it. Assume that these are the sides. That is a triangle here, another one here. The last two edges, yes. Assume that this is a triangulation for the given Delaunay sides, not the Delaunay side, I'm sorry, for the given set of points. And again, this is a maximum planar subdivision. Why is that? Since we cannot have any connection between, let's say, assume that this one here, you may connect this point to the other one above, but here you see you are destroying the planarity. So that's why we can say that this is a planar subdivision. The new edge, the new added edge, should be going through any over the edges available in the planar subdivision. So if that's the case, we can say that this is a maximal planar subdivision. Any questions, guys? So the maximum planar subdivision is simply actually the triangulation of P, in which all the vertices are the points in the given set P. So according to our previous definition, we know that once you are given a set of points, then we can easily obtain a triangulation. And obviously it will be consisting of triangles, and you can easily triangulate any given polygon, right? Assume that this is a polygon you have. You can easily triangulate it like this one, for instance. There are different options, but any polygon can easily be triangulated. And the thing is that the number of triangles and the number of edges you have in the triangulation is equal to any triangulation you have. If you have, let's say here, you see there are many points. Regardless of your triangulation, they will always have the same number of triangles and same number of edges. But the thing is that you shouldn't you should modify the points which are on the convex boundary of this point set P. This is called as convex hull. We discussed this issue, if you remember. If you have a kind of, if you assume that these points as the pins, and once you have a rubber, flexible rubber, and you put it around, then you will obtain the convex hull of this point set P. And if you do not modify the outer boundary, then we can easily say that any triangulation will have the same number of triangles and same number of edges. But one of them will be the Delaunay triangulation. We have many triangulations, but we have a unique triangulation whose minimum angles are maximized. So let's have a look at the first theorem regarding Delaunay triangulation. It states that once you are given n number of points on the plane, and we are assuming that they are not collinear, and k will be the number of points which are lying on the boundary. So if you look at here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 number of, in our example, k is equal to 9. They are lying on the convex hull of this given set of point P. And then we can easily say that any triangulation will have this amount of triangles and this amount of edges. And as you see, they only depend on the number of inputs and the number of points on the convex boundary. So we can say that we have a kind of a linear relationship. Now assume that tau is an example triangulation of the given set P. So I can say that this is a triangulation tau, and it has m triangles. So 1, 2, 3. We have up to m number of triangles, and that means we will have 3 times m number of angles in this triangulation. So now we are going to sort these angles from smallest one to the largest one. So as you see, we have the first angle, alpha 1, alpha 2, up to alpha 3n. Since we have this much angles, since there are n number of triangles, if you multiply with 3, we will have 3 times n number of angles in this triangulation tau. Now we are going to define an angle vector. This is the angle vector of our triangulation. And we are, as we have done in the previous step, we have an order in these angles starting from the smallest one to the largest one. So we may assume that this is 5 degrees, maybe 6, and then 6 coming, and up to maybe, let's say, 6 to 7. That might be an example angle vector of our triangulation tau. And for other triangulations, obviously you have different values. For instance, this, as I've drawn 6, 7, 7. This one might have 8, let's say 10, some other values. They will be a bit different, but obviously, since we have the same number of triangles, they will always have same number of angles in their angle vectors. So now we are going to actually compare these angle vectors. Which one is larger, which one is smaller? And we will be doing it in a lexicographical way. We will be comparing these two triangulations, their angle vectors, A of tau and A of tau prime, between each other, and check which one is larger and the other one is smaller. So now let's go into the details of this comparison, how we're going to compare these two triangulations in terms of their angles. Assume that you have an index I. It can be any index. It might be 5th or 6th, it doesn't matter. If you have such an index and if this is satisfied, then we can say that angle vector of the first triangulation tau is lexicographically larger than the angle vector of tau prime. So let's give an example. This one is larger, so assume that this is the angles we have. And the other one has such a thing, let's say. Assume that the rest is the same. So now let's have a look at a case where we have the angles equal to each other. This is then J, and this is I, okay? And this is I plus 1, I plus 2, okay? And I'm selecting this index. This is the index now I'm focusing on. If you look at here, yes, these are equal to each other. They are equal to 5. But for the next item, since I is a bit larger than J, it can, by the way, they may have the same, after I describe this one, I will give you another example. Here, I is more than J, the index I is more than J, and I can see that angle for the tau, this is tau, and this is tau prime. I see that this angle of alpha I is larger than alpha I prime. Yes, this is satisfied, so I can say that angle vector of tau is larger than the angle vector of tau prime. But the thing is that this requirement should be valid for all J values. If, for instance, let's say at a time here, you may have, let's say, 35, and we have, let's say, 37 here. If that's the case, then I can simply say that this is not valid. And we cannot make a comparison between these two. Since at this point, if you assume that this is J, and if you look at the I, you can say that this is not satisfied. So I cannot, if that's the case, I cannot say that tau prime is larger than tau. We cannot have a solid conclusion, but for most of the time, we will not have such difficult cases. We'll have always such examples. Again, let me have another one. For instance, you may have such a case. Again, so if you look at here, for instance, which one is lexicographically larger, we cannot again say anything. At this point, the tau prime is larger, but if you look at here, this part, this time, tau is larger. But as I mentioned in our examples, we will not have such complicated case. We will always have simpler ones, and you can simply state that one is larger than the other one in terms of angles. Any questions, guys? This might be a bit complicated. If you have questions, please feel free to ask.
Teacher, just one angle difference is enough to evaluate our case, right? Just one example is enough.
Yes.
Okay.
For instance, assume that these are the angles for the tau, and now I will have, for instance, like this one. So which one is lexicographically larger?
Is it first one?
The first one is larger, since if you look at here, they are the same, but the next one, for the next ones, tau has a larger angle than tau prime. So I can say that this one is larger than the tau prime, but for the rest, at least they should be equal to each other. Okay, this is the requirements, the only requirement we have in this comparison. So if you have an actually triangulation, and if the triangulation has an angle vector which is higher or equal to the other triangulations, we can say that this is the angle optimal triangulation of the given point set P. Now let's have a look at some primitive theorems. This one is about simple geometry. It's actually considering the angles. We have a circle C, and we have a line intersecting the circle, and some letters, some actually point vertices are on the circle, and we have a vertex inside the circle, and another vertex outside the circle. And we can simply say that the angle between A and B is larger than the other angles, and we can say that the angle between AP and B is equal to the angle between A, Q, and B. This is actually the simple theorem, simple geometry, and we will be making use of this theorem in the upcoming, let's say, cases. Let's have a look at another operation which we will actually need a lot in our triangulation. You see, we have the same size, Pi, J, L, and K, I, J, L, and K. But the thing is that we have an edge flip operation. Initially, we have an edge between I and J. Right now, we remove that edge, and instead, we have between L and K. So by simply checking the angles, you can say that this one is an illegal edge since its minimum angle is smaller than the other case. In this one, we have, as you see, larger angles, and the minimum angle probably assume that this alpha 1 prime. And if you look at the initial case, we have the smallest angle, alpha 4, and obviously alpha 4 is smaller than alpha 1 prime. And if you come up with any case, let's say convolution, you can say that this is an illegal edge since it's not satisfying the proper triangulations. In the previous slides, we said that our aim is always to maximize the minimum angle, but on the left-hand side, this minimum angle, which is alpha 4, is not maximized. Now we have more, angles, larger angles, with the help of this flipping operation, and we can say that the initial edge in between is an illegal edge. And in the next upcoming slides, upcoming part of this chapter, we are trying to find some ways to get rid of these illegal edges.